In this video, we're going to study the order statistics of the uniform distribution. First, some basic ideas around this concept. Suppose we obtain n measurements of a random variable x following a certain distribution and order them from smallest to largest. We could repeat many times this experiment of measuring n times and then sorting. We would get each time a random value for the smallest measurement in the series, a random value for the second smallest measurement in the series, a random value for the third smallest measurement in the series, and so on. Each of these ordered values is a random variable, and we will use the notation below. For example, x sub 1 between parentheses is the minimum, and x sub n between parentheses is the maximum. We ask ourselves what distribution each random variable follows. In general, the distribution of the kth order statistic. In this video, we solve this from measurements sampled from a uniform distribution of parameters a and b, and study the connection to the beta distribution in the case of sampling from a uniform distribution with parameters 0 and 1. A uniform distribution of parameters a and b can be characterized using its cumulative distribution function, which is the one you can see here, or we can also use the probability density function that you can see here. The kth order statistic will also follow some distribution, and there exist general formulas in terms of the CDF and the PDF of the distribution from where we obtain the original samples. The CDF of the kth order statistic is the one you can see here, and the PDF of the kth order statistic is the one you see here. In this video, we will specifically compute the PDF since that is enough to characterize the distribution. Now, in our case, we obtain measurements from a uniform distribution. The PDF of the uniform distribution has three parts: for when x is less than a, for when x is between a and b, and for when x is greater than b. Therefore, the PDF of the associated kth order statistic will also depend on these intervals. We will substitute in the general formula the specific pieces of the CDF and the PDF of the uniform distribution in each interval. For x less than a, the PDF of the kth order statistic takes the value 0. For x between a and b, the PDF of the kth order statistic takes the value you see here after some manipulations. For x greater than b, the PDF of the kth order statistic also takes the value 0. In summary, this is the PDF of the kth order statistic in the case where we sample series of n measurements from a uniform distribution with parameters a and b. Let's take a closer look at a particular case. Consider a equal to 0 and b equal to 1. That is, we sample from a uniform distribution of parameters 0 and 1. The specific PDF is the one you see here. We are going to see that this case has a close connection with the beta distribution. First, recall the definition of the beta function. When its arguments are positive integers, the integral takes the value given by this expression with factorials. Now, in particular, consider the beta function with arguments k and n minus k plus 1. It will take the value k minus 1 factorial times n minus k factorial divided by n factorial. Notice that this is precisely the inverse of the constant that we had at the front of our PDF for the kth order statistic. Also, looking at the exponents, we see that the PDF of the kth order statistic matches perfectly with the PDF of a beta distribution with parameters k and n minus k plus 1. And thus, we conclude that the kth order statistic follows a beta distribution with parameters k and n minus k plus 1 if the n measurements of each series come from a uniform distribution of parameters 0 and 1. This is an important result because the beta distribution is well known, and we already know in advance many of its properties. Or at least we can easily look them up in a lookup table. For example, if we want to compute the mean or the variance, we do not need to set up the integrals because these moments are already tabulated. You can see on the right the mean and the variance of a beta distribution for any two parameters alpha and beta. In our case, with parameters k and n minus k plus 1, the mean will be k divided by n plus 1, and the variance will be k times n minus k plus 1 divided by n plus 1 squared times n plus 2. As an example of application, let us compute these quantities for the first order statistic, which is the one we obtain with k equal to 1, and assume we make n equal to 5 measurements in each series. That is, in each series, we obtain a sample of 5 measurements from a uniform distribution of parameters 0 and 1, and we keep track of the minimum value of each series. After repeating this experiment for many series, what mean and variance should we expect to see? Well, setting k equal to 1 and n equal to 5, we know that the minimum value of each series of 5 measurements follows a beta distribution with parameters 1 and 5, which, by the way, corresponds to the PDF that you can see on the right. So we just plug k equal to 1 and n equal to 5 into the formulas above, and we obtain a mean of 1 over 6 and a variance of 5 over 252.